Good morning, my name is Mike McDonald. I'll be teaching this class about supercharged CNC programs with optimization software. So what does optimization mean? So the term optimal meaning the best or most favorable way to do something or to achieve or do something. So you always want to be the best. So what does optimization mean in the manufacturing? So reducing your NC run times, getting parts off the machine faster, making parts cheaper, increasing your delivery. So who should be optimizing? Who needs to optimize? Well, pretty much everybody, if you want to compete. So what does the term compete mean? It's to strive to win something by defeating, establishing superiority over others who are trying to do the same thing as you. So we're all trying to get that best, be better than everybody else. So signs that you may need to optimize: you're missing your delivery dates. You're losing bids. Losing contracts. You've already got the contract, now something new's come up and you don't have it anymore. And then ultimately you're declining profits. So unfortunately you have to go through all of those to find out that this is the problem, and hence you're looking for how can I increase, how can I make more? So I know what you're thinking, so I've given you some options there. So you're thinking, is that all you got? Well, actually just reducing your NC run times, getting your parts off faster, making them cheaper, increase delivery. What if we could add more to that? How about we improve your part quality, more consistent results, less time deburring, longer tool life, you're not breaking cutters, and less wear and tear on your machine. So if you can run a part in 3 hours instead of 4 hours, well, your machine is running less. If I'm getting that part off in a more favorable way, then I'm not beating up my machine as well as saving time. So, little information about CGTech. We've been around since 1988. We're in 12 different countries. We are the leaders in NC verification optimization. So 30 years of partnering to be more competitive. Typical manufacturing workflow, starting off in the CAD/CAM area, working our way across. Eventually, after you write your NC program, it goes into verification and then optimization. You get all the bugs worked out. It goes back and forth between your CAM system, run it through Vericut, you find your issues, go back into your CAM system, make corrections that you've got, get all the bugs worked out, then you can optimize your program. That's what we're talking about today, optimizing. So that optimization then comes in. How can I take that job that I know runs good and make it run even better? Well, some of the common optimization strategies are to change the way you cut parts, such as new CAM system, trochoidal type cuttings, things like that. Maybe a new machine, high speed, that's taking care of business for you. Or maybe new cutting tools. All of those things are good ways to get started, but there's even more. So some of the other cutting paths, dynamic milling, volume mill, eye machining, profit milling, all different types of material removal methods that we've proven in certain instances do work better depending on your material removal of the parts that you've got. So things, we call them silent killers of manufacturing, things that are hurting you while you're running. So if you've got a well-oiled process, but you don't have enough oil, these are some of the things that can happen to you. Your tools load up, you're burning up tools, poor cutting methods, you're either over-aggressive or even under-aggressive. So if you're not aggressive enough, your tools will rub and wear out. Your bad part finishes, chatter in the corners, things like that. So optimizing those NC feed rates, and that's how our optimization works. We're looking at maintaining a constant chip load. So which NC programs make the best candidates? Well, milling and turning. We can optimize either of those. So any existing NC program, and the reason we say that is because we're using and processing the G-code file. We're not actually utilizing the CAM data. Is the post-process data that actually goes to the machine. So what's the answer to this? How do we achieve this optimization? Varicut force optimization. That is the answer. So our optimization is physics-based. We actually cut materials. So we've got a database of 130 plus materials, titanium, high tensile steels, aluminum, brass, whatever it happens to be. We've cut these, used a dynamometer to verify what the cutting forces are when you're actually machining a piece of material, and those go into the algorithms that are used to help this. Along with that, we take what is the actual cutter made of, not just the material we're cutting, what are the helix, what's the rake angle, that type of information, so we know all of the pieces to the puzzle. So this is force optimization. While it's cutting, we've got graphs that show you exactly what the cutting conditions are. So as you see this going up and down in the graph here, that's your cutting conditions changing, So talking about the physics, if you look at the material hardness, the cutting tool, the CNC limits, the NC program, all of those things that come together right where this bullseye is at. Everything happens at the tip of the tool. So how do we manage all of that, all of these things going on at one place all at the same time? So we want to maintain an ideal chip thickness. Right now, we look at things and we say they're upside down because we choose one particular feed rate and the cutting conditions are all over the place. So, and that cutting condition changes. I know with our CAD/CAM systems, we tell it what chip load we want to cut at. And that's fine if you're taking a full cut just like this. If I'm getting 90-degree cut there, I'm gonna get that full chip load exactly the way the manufacturer expects it. But the reality is that we're not always cutting a full 90 degrees and getting this chip load here. We're cutting a smaller portion and we're ending up with a chip load that is something down here smaller. Well, so now we're underutilizing our cutting tools and we're taking longer to cut that part. So what if I could speed this up so the chip coming off of here is the size of that chip right there? That's what our optimization, force optimization, is doing. So we want to maintain constant chip thickness that's correctly matched to the cutter that we're using. So we start off, well, where do we get this information? We could have gotten it right out of the machine catalog from the vendor, or maybe we have some information from history. We've cut these parts before, we know what works good. Either way, you need to come up with that perfect calculation for what I should be cutting, how I should be removing that piece of material. So the result of an inconsistent chip load is what you see in the images here. So a thin chip, not taking a big enough bite, it's actually rubbing the part. And something more aggressive is going to either chip or could cause chatter on your part. So you're going to end up with excessive tool wear. Not only your surface finish on your parts is going to be not the quality that you're looking for. So keeping the chip thickness maximized is what force does. We maintain the constant chip thickness by increasing and lowering the feed rates as the material's being removed, using that tool to its full potential. So benefits include, when you do this, substantial time savings, 20 to 30% on average, better surface finish, improved tool life, less hand and bench work needed, and less wear and tear on your machine. So just a simple example of a typical cut, small cut, medium cut, heavy cut. Either way, in your CAD/CAM system, you've chosen one feed rate. So although they can vary in some instances, most of the time that's just a single feed rate, removing the entire material from that pocket or that area of your part. So faster feed rates equal opportunity, opportunity equals savings. So typical NC program outputs a feed rate per cutting operation. So you choose that pocket or that periphery or that area of the part that you want to cut. You choose a feed rate based on the type of material you have, the type of tool you're using, and how you want to remove that. The problem is that's really upside down. What we're doing is well, in today's NC programs, the feed rate's fixed and the chip thickness is all over the place. So, but we really want the opposite of that. We want that chip thickness to be constant and allow us to move the feed rates all over the place. So here's a graph from Inside Force Charts, or Inside Force Optimization, and you can see the chip thickness here is kind of bouncing around. But if you look down at the lower graph, the feed per minute is constant. That's how it comes out of the CAD/CAM system. So what if we could change all that, change the feed rates, and make the chart look like this? So our chip thickness is straight across the top, maintaining that constant chip thickness, and change the feed rates all over the place. Your tools last longer, your part surface finish is better, everything is better. So if you look at the NC code here on the left side, you can see that the feed rates are changing all the way down because we've optimized it instead of just choosing one feed rate and having our chip load all over the place, wearing out our tools prematurely. So looking at this comparison, you can see that the area above, we call this opportunity where the dollar signs are at there, because we're actually going to increase those rates, make that program run faster. It isn't always about how fast can I push this and make it run. We're maintaining that chip load per the manufacturer or per your known values that you can cut with. This is a comparison of the two different programs, the original program on the left side and the Force Optimized program on the right side. So you can see we've got some gaps in here. Well, these gaps are where we've taken this line of code and we broke it up numerous times to change the feed rates because the chip thickness is varying. So we bring that feed rate up, we straighten that line out, get a more constant chip load, and we do that with knowing the cutting conditions and increasing the feed rate along the way. So looking at these two charts, these two graphs out of force, you can see the blue one here is the fixed feed rate and it varies coming down over here, and you can see all the spikes in my chip thickness there. And if you look at the chart on the right side there, it's showing me a more constant chip thickness and the feed rate is all over the place, which is not upside down. That's where we want it to be. So the reality of changing cutting conditions, it's impossible for somebody, or I should say, it would be next to impossible for somebody to go in and monitor their entire tool path, looking at the tool cutting conditions and making that change to each and every line of code to do that. That's why with VeriCut and Force Optimization, we're continually monitoring those cutting conditions and make those changes on the fly. So here's an example of how cutting conditions are changing while a part's being cut. You can see the black areas here are actually the engagement. So it's a little bit up on the right side, a little bit less here. As it comes around the corner, it gets deep in there, and those cutting conditions are changing. You wouldn't want one single feed rate to handle all those different cuts. You want to break that up, get that perfect chip, make that cutter last longer, run that part faster. So cutting conditions changing require that increase and reduction in feed rate. It isn't always about speeding things up. There are many times when programs are overly aggressive, so we have to slow them down. We have times when we lose a little time on something because something is programmed too aggressively. So force optimization, your cutting tools typically are underutilized. What constitutes a good program? Well, you didn't break a tool. You actually made a good part that made it through inspection and it's okay, but do you really know that it's optimal? And that's what we're achieving here. We want that optimal. How fast can I really get these parts off the machine, good parts, not just get them off? I don't want to spend more time in the bench department. So if we can optimize this, getting an ultimate chip load, better surface finish, faster parts, so you're saving 20%, that means every 5 parts you get one for free. here's a simple example. This is a real part that we actually cut. We hired somebody to program this, so we're using real feeds and speeds. It's a piece of titanium, 6AL4V. So you can see the different cutting conditions are going to change as it goes around here. It's an aerospace bracket. And again, the graphs showing the different cutting conditions. So inside here we can actually choose information in the graph. We can select that in our review mode, and it'll actually update the part to that particular time when it's cut. So if you see a spike or a lull or something that brings to concern, you can select that and actually look at it exactly where it's being cut inside VeriCut. It actually re-updates the part material to exactly when that cut was happening. So you can see our chip thickness here is all over the place. We've got our feed rates. I've got information here from the original program. In the optimized, we can actually see both of that. The original information is here. The optimized program is showing me, I can see my radial width is different, the total forces, how much that piece of material is pushing back against that cutter as we're machining it. So we've got a lot of information here. We can check for tool deflection, lots of things going on. A lot of people don't really realize what's going on when they're actually cutting a part. You know, am I making a good part is their ultimate goal, of course, but am I optimally making a good part? That's what I want. So at the end of this process, running your force optimization, we have an optimization savings calculator that shows you what the original runtime was, the optimized runtime, what the time savings is, and if you want to add in some information to calculate and see what savings on a whole run of these parts or what your shop might save on average, you know, how many machines, how many hours a day do you run, that kind of stuff. So you can calculate those as well. So here is that part that I just showed you. These are real numbers. We actually saved, it was actually 37 point something percent. So let's round up, in this case, 38% savings on this particular part. So force optimized program showing the upper area in the bright green is where we increased everything, our opportunity, our savings, our time savings there. You can see the difference as it's cutting. The blue line is the original program. The red lines are the optimized stuff. So looking at the data on the left side, you can see where we've got different chip loads and different feed rates going on here versus in the optimized. So you can actually see what are the changes that are actually happening as I'm running this. So target FZ being your chip load. If the target's never reached, you know, this is that opportunity that we're missing out on. So what does VeriCut know? What kind of information do we need to put inside of VeriCut into force optimization to allow it to accurately do this? Well, looking at the first line, the cutting tool properties, we've keyed in the number of flutes, the helix angle, and the rake angle. Most of this stuff we can get automatically right from the tool vendor. And then the cutting tool properties. Is this carbide, cobalt, high-speed steel? Is it an inserted tool? Because all of those things play a factor in this material moving process. So block by block interaction, VeriCut knows continually when it's removing material, how much material, what that chip load is, so it knows when to speed up, when to slow down. You're too aggressive, you're not aggressive enough. Find that happy medium, and that end result is, again, faster running parts, better surface finish, tools last longer. It's a win-win-win situation. So the power of knowledge, and that's where these graphs come in. You know, those graphs are telling you the story that typically you know because it squeals when it goes into that corner. Okay, yeah, that's too aggressive, but it didn't break the tool and I can clean it up and bench. So yeah, it's probably okay, but it doesn't have to be like that. So if we optimize that, we know it's taking too much material in that corner. We can slow it down based on that chip load and actually give you something good. So different options inside the force graphs, total force, radial axial force, machine, radial width axial. There's a lot of different graphs you can see. Today I've been showing just a few of those that I like to use when I'm optimizing something, but sometimes you need other stuff to give you more of that story. All right, well, we can also optimize turning parts. So you think about turning parts, you got constant surface feed, and that pretty much is constant. So where does the savings come in? So if you've roughed out a part and you've got it stair-stepped from your roughing operations, and then you come in to finish or semi-finish, those cutting conditions are going to be changing on you. So we've proven with force optimization in turning that we end up with a better surface finish, better parts, faster running, tool life lasts longer. You know, turning does not like intermittent cuts, so if I can maintain that chip load and keep that tool cutting more constant, it's going to save my tools. So you can see here in the graph on the right side there, faster and safer. As I mentioned, it's not always about speeding things up. In this case, you can see all of the red there. The program was too aggressive, so we backed it down based on feeds and speeds. So more benefits from force optimization. Part temperatures change. You're cutting tool temperatures with force, so as we maintain different forces and cut back on our chip limits, we don't, or on our chip thickness, we don't accidentally work harden our part. So those are benefits automatically that you get from maintaining a constant chip load. So everybody's making improvements, not just us, not just Verica CGTech with our force optimization. CAM softwares, I showed you some of the different cutting methods earlier here. Cutting tool manufacturers, they've got new coatings, new configurations of old tools, different helixes, those types of things. They're also working to, you know, make improvements along with Vericut force optimization and machining tools, rigid structures, better tooling, better things to hold your parts as well. So in summary, what do we get? So when we optimize this and change these feed rates to give us a constant chip load, you know, we get rid of those longer run times and that excessive tool wear. Extra wear and tear on the machine goes away. All of those things go, and they end up with a final result is 20 to 50% time savings. Your cutting tools last longer. People just assume that your cutting tools, it's a given. I'm going to have to buy them and spend them, but they didn't realize until force optimization that actually they can make that tool last a whole lot longer than it used to. So visible crisis, hidden missed opportunities, you know, having the ability to see what's in the background, or in this case below, and that's what these graphs give you, to see what's really going on at your machine while something's being cut. So force optimization, the way I look at it, your CAM software only starts the job, but the force optimization software comes in and finishes it. Thank you very much.